Greetings, Brainy Bunch. We're going to look at the beginning of the lab in this video. That lab concerns various objects as they roll down an incline without slipping. That is a very important part because that allows us to connect the speed of our center of mass to the rotational speed or rotational velocity through multiplying it by radius. Once slipping starts, that no longer holds. One other thing to remember is that force of friction, static in this case, is the one that produces torque. It still equals mu static times normal, but on top of that now we're going to say that the torque is produced by that specific force, so force of friction static times radius. First question, determine the translational kinetic energy of the sphere. Now remember back when we had just objects that were sliding without friction for that matter, we would say if we have a box, for example, that is sitting at the top of an incline, force of gravity would be responsible for accelerating it down the incline, and we would say that mgh would be equal mgh initial for that matter because we start with initial height, which would be this. Initial gravitational energy would translate into final kinetic energy, like so. And that was pretty easy. This type of question could be complicated by saying that there is friction, and in that case we would have said mgh initial plus work of friction would be equal to the final kinetic energy in the end. And this speed would be less than that speed. In this case, however, friction is not robbing us of kinetic energy. It just transfers it into a different type of energy, which is also kinetic, but it's called kinetic rotational energy. And that's what we're going to work with in this video. And that's what you're going to be working with in your lab. Initial gravitational energy is equal to the final translational energy and rotational energy, both of which are kinetic because the object is moving. Then we're going to apply the formula mv squared over 2 plus I, which is moment of inertia or rotational inertia, times omega, which is our angular speed, squared over 2. Because there's no slipping, we can say that V equals omega times R. But since we're after kinetic energy that is translational, we're interested in V rather than omega. So instead of V equals omega R, we're going to flip this and say omega is V over R. And then plug that into the formula for rotational kinetic energy, which will render us mv squared over 2 plus I, and then I'm going to say V squared over R squared. Furthermore, what is I? If we're working with a uniform sphere, then I is 2/5 mr squared. So that would translate into mv squared over 2 plus. Now, so that we do not lose this 1/2, I'm going to put it in front. Then I'm going to replace I with 2/5 mr squared, and then multiply that finally by V squared over R squared. A little bit cramped up. So now I'm going to consolidate that to UG equals mv squared over 2 and then mv squared over 5. Hello, middle school. Common denominator being 10, 7 mv squared. If what I wanted to find was V, I would use this formula. However, what they're asking about, what is the kinetic energy? Now let's dissect this 7/10 mv squared. You know that kinetic energy translational is mv squared over 2. Now we should have 7 over 10 instead of 1/2. So if I multiply this by 7/5, then I'm good to go. Again, this is kinetic energy that I'm after. And in relation to my original UG, I can say that kinetic energy translational is 5/7 of UG. Then determine the rotational kinetic energy of the sphere. Look how UG comprised both of them. So then kinetic energy translational turned out to be 5/7 of UG. Then the leftover, which is 2/7 of UG, would be kinetic energy rotational. We did not even have to recalculate much. Question 3, we need to figure out the acceleration. We have to apply Sir Isaac's law twice. We know that, again, if I drew my object on the incline, I would have gravity, force of friction that way, and normal that way. And force of gravity x, which is the center of mass of my object, is accelerating in that direction, which tells me that mgx minus force of friction, static, would be equal to ma. That's the question. Well, I know what mgx is. It's mg sine. That's easy. And if I can figure out the parameters of my incline, I'm good to go. However, what's force of friction? I don't know what force of friction is. Oh my goodness. Back to here. Remember how we said that force of friction is the one that gives us angular acceleration. So force of friction times radius, because that's our lever arm, should be equal to I alpha. Again, if there's no slipping, I can connect alpha to A, which is the acceleration of the center of mass. It's going to be I times A over R. Boom. Now let's put this together. I is 2/5 mr squared, because this is a solid sphere, times A over R, and it equals F times R, force of friction, pardon me. This R goes, and then that R goes, and we end up with force of friction being equal to 2/5 ma. So then, what do I have? Going back, mg sine of theta minus 2/5 ma should be equal to ma, from where mg sine equals to 7/5 ma. M cancels, and then A is 5/7 of g sine of theta. Boom. Then determine the force of friction acting on the sphere as it's rolling down the inclined plane. Going back to what we stated, mg sine of theta minus force of friction should be equal to ma, from where force of friction is m, and then we have our g sine of theta minus a. Remember, I grabbed this to the right, that to the left with a minus, and then just consolidated it. A is 5/7 of g sine, so force of friction. So then I can take my g sine out, and then I have 1 minus 5/7, meaning that force of friction is nothing but 2/7 mg sine of theta. And then finally, when the solid sphere is replaced with a hollow sphere of identical mass and radius, how would it change the result? To question B. Explain. So what would solid sphere versus hollow sphere change? From 2/5 mr squared, we're going to 2/3 mr squared. A hollow sphere has a greater rotational inertia. It is harder to rotate. So as I increases, omega decreases. MGH will be the same. MV squared over 2 plus now 2/3 mr squared times omega times V squared over R squared. Boom, boom. And we end up with MV squared over 2. And look at that, I forgot that 1/2. Boom, boom. Plus MV squared over 3, which is common denominator being 6, 5/6 of mv squared. Now look what happens. MGH is equal to 5/6 mv squared, which is mv squared over 2 times 5/3. So new kinetic translational energy is now 3/5 of mgh. Before it was 5/7, and now it's 3/5. So just to compare, kinetic energy translational was 5/7 of mgh. Let's say our original UG is 35 joules. Translational energy for this sphere will be 21 joules, whereas translational energy for the sphere that is, so this is our hollow and this is our solid sphere. So then translational energy for the solid sphere is going to be 25 joules. So a solid sphere is faster. If you raced a solid and a hollow sphere down an incline, the solid sphere would have won.